The last thing we need to talk about is what we call the change of base formula. And the change of base formula is useful when, say, we have a quantity log base A of X. But I really want to write that quantity as another log base. I don't want to use base A. I want to write it with a different base. Let's try that. So what if we start with y equals log base A of X, right? My goal is to see if I can write this with log base B. What I'm going to go ahead and do to start is I'm going to convert forms. And when I do that, I can get the equation. Let's see, I would get A to the Y equals X when I convert that into an exponential equation. That's what I mean by convert forms. All right, I have A to the Y equals X. I have two things equal to each other. And turns out if two quantities are equal to each other, then if we put them as arguments into the same log base, they're also going to be equal. Here's what I mean by that. I can take log base B of both sides, and they're still going to be equal. So if I put my right-hand side log base B of X there, and then log base C of A to the Y, those are going to be equal to each other. I can do that on both sides and we'll get equivalent things. And now I have inside of a log, I have my argument is base to a power, right? I have this power here, which maybe I can bring that up in front. So maybe I can write that as y times log base B of A is equal to log base B of X. And this is starting to look really promising to me because now I only have log base B in here. I no longer have any log base A's. One thing I might do now, remembering that Y was actually the thing that I was solving for, I might divide by log base B of A, divide by this quantity here, in order to get Y by itself and say Y equals log base B of X divided by log base B of A. And if I just now replace that Y was equal to log base A of X, I can write this as log base A of X is equal to log base B of X and log base B of A. So that's what we call the change of base formula. And what we see here is that if I have log base A to start with, I can write it as, I need to use two logs. I need to use log base B of what my argument was, and then log base B of what the base was. So I have to divide two logs, but I've written it entirely in terms of a different logarithm. And this works for any base. It's particularly useful for our most common logs, our common log and our natural log. So I might say log base A of X is equal to, we could use just the common log base 10, and say log base A of X is equal to log of X divided by log of A. I can also do this with my natural log and say, what if my base was E? Then I could say that log base A of X was equal to log base E of X divided by log base E of A. So let's try that in an example. If I have log base 5 of 8, we can't come up with just a nice answer for this because 5 to a power equal to 8. There's not a nice number. That's not a rational number that will do that. And you might have noticed that your calculator might not have a log base 5 button. It probably has a log base 10 button, and it has an ln button, but it probably doesn't have a log base 5 button. So if I wanted to know approximately what log base 5 of 8 is equal to, I could calculate this as, maybe I could use my log button and say it must be equal to the log of 8 divided by the log of 5. Or I could use my ln button and say it's equal to the ln of 8 divided by the ln of 5. And if you go to a calculator and you write log of 8 divided by log of 5, you'll get that this is about, I should remove that equals and put it as an approximate. This is about equals to 1.29202. So try that out on your own calculator. And it's also true that if you change it to the natural log of 8 and use the ln button and divide by the ln of 5, you will also get 1.29. So try that on your calculator to make sure you can do that. We can do the same kind of idea for log base 3, right? There's not a log base 3 button. I could write this as log of 20 over log of 3. Or if you like your ln button, you can write this as the ln of 20 over the ln of 3. And when you put that in a calculator, ln of 20 divided by the ln of 3, you're going to get something that's 2.7268. And these go on. They're irrational numbers. Before we go on, I want to pause and say, does this make sense? Does the number of 2.9 or 2.7 ... make sense? And I think it does. Even though we can't always calculate these logs exactly, sometimes we can kind of estimate what they should be. Like, I know that 3 to the second power is 9, and 3 to the third power is 27. So if I need 3 to the some sort of power equal to 20, it makes sense to me that my answer should be somewhere between 2 and 3, because I need 20 to be somewhere between 9 and 27. So an answer of 2.7 makes some sense to me. Similarly, if we think about A, I know that 5 to the first power is 5, and 5 to the second power is 25. I need an answer. I need 5 to a power to be 8, which is in between 5 and 25. So it makes sense that my answer for my log is some sort of number between 1 and 2. And that's usually as close as we can get to kind of just a rough estimate for a log. I think this helps us get an idea of what these numbers should be approximately, or at least get a range for them, and then use the calculator for the approximate answer. Okay, so I want to come back up here and just say, why do we need this? One, it's because some calculators don't have those buttons. Most calculators only have a log or ln buttons, or if they have a log of a different base that you can type in, it's kind of cumbersome to get to. And sometimes it's easier to just use this formula to get a decimal approximation rather than trying to find it in the special features of your calculator. The other reason why I think this is really cool is a little bit more complicated. And I might think about just for a second of like this equation right here. If I think about log of A of x, log base A of x, and that's equal to log of x divided by log of A. Well, log of A is just a number, right? I would think about this using for a particular x. Maybe I'm thinking log base 5 of x, right? Maybe my A was equal to 5. And so log of A is log of 5. It's some sort of number. I could put that in my calculator and say, what is log of 5? In fact, let's see, what is log, I'm doing it on my computer here, log of 5. It's about 0.698, okay? It's just dividing log of x, taking my log of x and dividing it by some sort of number, okay? Dividing my function by some sort of number is a translation. It's a vertical stretch or shift, depending on if the number is bigger than 1 or less than 1. So I'm going to write down why this matters, and then I'm going to show you. So the other reason why this is cool is that every log with any base is just a translation, a vertical stretch or shrink of our log x or ln of x. And actually it's both of them, but a different stretch on both of them. And I want to show you that in a graph. So before we go, I'll just remind you that the way that we got from one to the other was dividing by a log, right? And what I have plotted here, let me turn some of these off. What I have here is thinking about log base 5. So that's my log base 5 of x graph. I also have looked at this. It looks a little weird right now. I'm taking log of x and dividing by h, but you see down here that my h is just equal to 1. So right now, this is my just log base 10 graph. And I also can look at my ln graph. And again, I'm dividing by just 1 right now, so that is just ln. And if I put them all 3 here together, they are similar right? But they are not all the same. We have similar behavior. We all go through that point, 1,0, but the blue one is maybe bigger on both sides. The green one is smaller on both sides. So I'm going to turn the green one off for a second. And the idea is I can turn my LN graph, I can turn that blue graph into the red graph by just dividing by the right number, which I think is probably log of 5. Let's see, what I'm going to do is I'm going to move this k on either side. By changing k bigger and smaller, I'm dividing by a bigger and smaller number. And really, I am stretching my graph. And what we see here is if I can make k, see how they're the same? Oh my goodness, I've made them the same. And that's probably the value of the ln of 5 right there. So I can turn my ln graph into my log base 5 graph by just dividing by the perfect number. Okay. I can do the same thing with my log graph, log base 10. I can turn this green graph into the red graph by dividing by the right number. So if I make h bigger, I'm getting further and further away, but if I make h smaller at about 0.7, see how they're about the same? And do you remember a little bit ago, we checked what was log of 5, and log of 5 was about 0.698. So that's about approximately, this isn't exact right now. But the idea is that I can translate my log graph, log x, or log base 10 of x, and I can translate my ln graph and turn it to any other log base that I want. So really, we have, all these different log graphs, but they're really essentially the same one, right? No matter what base we have, we can think about it as your regular run-of-the-mill log or ln. It's the same function, just translated. And I think that is pretty darn cool.